You ready?
Yep.
All right. So answering this one, the degrees of unsaturation, we're going to use the equation we have done before. So we're going to go 2n plus 2 minus h, and then divide by 2. So 2, 7, because the carbon's up there. And then we have our plus 2 minus 12, and then divide by 2, and that's going to give us 16 minus 12, 4 over 2, which is 2. So that means there's 2 degrees of unsaturation. And from what we have known before in class, a ring is 1 degree, a triple bond is 2, and a double bond is 1. So we can have a ring and a double bond. We can have 2 double bonds. We can have a triple bond. We just have to add them up properly. So pretend that you don't know the structure yet, even though we all know you do.
Mm-hmm.
And then how many non-equivalent carbons does A have? So this basically wants us to show that it basically wants to show us that none of these are unique. So if we're going to draw the group, we need to draw them all unique. So 1, 2, 3, 4, 5, 6, 7. So there's no symmetry. I know you might think that these are the same, but in reality there's no symmetry because of this double bond. Because that's why that double bond has to be inside. It can't be outside, because then if it was outside, you could have symmetry, and that wouldn't give us 7 non-equivalent carbons. So then it asks, what functional group is present in A? You can honestly just say it's an alkene because of the double bond. And then in the box provided, draw a structure. So just draw this structure and label the carbons with chemical shift data down below. And also, the reason we were able to find this 7 is because if you go down here to our C13 signals, so these are, whatever. So 1, 2, 3, 4, 5, 6, 7. That will give us our answer. So that's where we got our answer from. We didn't just pull it out of thin air. I know it kind of seems like we were just trying to get to that answer, but we got it just from that data. So use the data down there. Mm-hmm. And then what functional group present, the double bond, and then the chemical shift data. So this is the chemical shift data over here. And so if we look at this, we can see that this is CH2, CH2, this is just a C, this is CH3, this is a CH, CH2, CH2. So the only one that we're going to have that's down is the CH2. And so how many CH2s are there? 1, 2, yeah. So all these that are down are the CH2s. So let's look at this 141. You'll notice how it's not in here because the C, the DEPT, or the DEPT, can only track CH, CH2, and CH3. It can't track a single carbon with no hydrogen, and you'll see it can't track that one. So we realized that this one has been cut off. So we're going to put the 141 there. And then the next highest one is going to be the 121, and you can also see, because kind of the chemical shift data that has been shown over there, that chemical shift data will show us that the double bonds are relatively high. So,
and that's in page 600, 657.
Yeah. So then we realized that, so this is 141, this is 121, or 124. Okay, and we just get that data from down here. And so then we're going to put the lowest number on this carbon away. I can't remember why. Do you remember why?
Because it can't detect it very well, because it's a methyl. And so it's going to be the lowest, and like for stability, like when you have the highest one, you'll need like the lowest one next to it. So the lowest one out of them will be here.
Okay, but then, so going around the ring is kind of backwards. So we're going to do the next highest. So 141 is going to have 36. 121 is going to have the second highest, so 33. And then 36 is going to have the next highest, 30. And 33 is going to have the second highest, the 28. So that's how we kind of go about the depth signals. And that's what we can get from our data. We have not answered the extra credit because it's been a long day, and we're not going to answer it.
Okay.
So have fun. Bye.